Alrighty then, let's go ahead and talk about the isentropic efficiencies of turbines and compressors. As you know, compressor is kind of like the reverse of a turbine in terms of thermodynamics, right? And also I want to add here is, you can also add pump over here, because when the working fluid is a gas, we call this compressor. When the working fluid is a liquid, we call this a pump. In thermodynamics, we can extract much more energy from gas, so that's why we focus onto the compressor, okay? But at the end of the day, this will the approach that we have established will be applicable to a pump too, okay? So this is coming back from module 5. I'm not going to teach the whole thing again, but basically the turbine is an energy extracting device. I have one inlet, one outlet, and I extract energy from it, typically in terms of the shaft power, and I hook up this to a generator, and then the generator is converts the shaft power into the electricity that we can use in the towns and etc. Right? So that's a turbine. And at the same time, I want to also draw the compressor, and you will appreciate you see, it's like the reverse of it. I still have M dot over here. I should have used another color so that I can differentiate turbine and a compressor, but oh well, I can change the color. So let me change the color. I'll be right back. There we go. So from now the dark green one will be focused to the compressor. Okay, the compressor is the other way, right? So I put energy into it. So in here I have energy out. I have energy in. We typically talk about power, but it doesn't really matter. Okay, and here's you can imagine the compressor in your refrigerator. I mean, you're paying for it, right? I mean, to run the refrigerator, if you unplug it from the wall, what's going to happen? It's going to stop, right? So because the compressor needs power input. Okay, so what I want to do is I want to well, let's use a neutral color because I want to represent both from q.net minus w. What am I writing over here? Tell me. Yes, I hear you. You said that it is first law. That is true. VH squared plus GZ exit minus H inlet plus V inlet squared by 2 plus GZ inlet. Okay, I finally make it. So adiabatic, that's out. So typically, this is different than the nozzle, the previous segment. The velocity is not going to change tip the scale at all. Okay, it's too small compared to the H, because I typically use in a turbine, especially I use superheated steam. So this H is basically the VE squared divided by 2 is a joke compared to the HE. Okay, so that's why I'm neglecting that. So depending on the application, so I extract. So let's use this black. So in this one, this is going to be W out for a turbine. So this is a turbine. Okay, and I will have, I said green. So this is going to be a negative W in for the compressor, but the formula is the same at the end of the day. Okay, let's go ahead and write the simplified version of it. So for a turbine, let's write in the black font, turbine. What I do get is this W8 is a positive, so there's a negative in front of it, and I want to write the right hand side negative, not left hand side, because I want to leave it like that. W dot out is equal to M dot HI minus HE. And I want to say, you know this from module 5, this HI is always not much, but higher than H exit. So which means that the difference between these H values is going to give me the energy that I can extract. In this case, it's the power that I can extract from my system. Okay? And assuming this is a compressor, again, it is the other way around. So now I have a W dot in. Note that there's a negative in here, there's another negative in here, so that becomes a positive. So I simply write the right hand side without multiplying by a negative sign. H exit minus H inlet. This is the reason why I'm covering them together, just to save time. Okay, cool. So let's also now establish the turbine efficiency. Actual work, just like the nozzle, there's no difference there. So this is the actual work or power. I usually use power, but that doesn't really matter. They're proportional. Isentropic work or power. Okay. The reason why we write this form is this. I want to have something between 0 and 1. We are used to it, right? So isentropic is going to accomplish the extraction of the maximum energy. So let's say that this is 1000 watts, right? So this is going to be 900 as an example. So I'm going to get 0.9 in that case. That's why I'm writing this way. Why am I explaining this? In a minute when I write this, you will see what I mean. When I write this compressor, you will see what I mean. I still want to get between 0 and 1, okay? But anyways, so let's write this. M dot times, for turbine, HI minus HE, let's call this actual, divided by M dot times HI minus HE and isentropic. M dots cancel, so I get myself, this is HI minus HEA divided by HI minus HES, okay? And in order to define this guy, what I have to do is I have to have two, because of the state postulates, independent properties, right? The first property is S1 is equal to S2, not good enough. So I'm going to do just like I did in the, I will be consistent, and I will take the pressure between the actual and the isentropic process to be the same. This is the exact same thing what I did for the nozzle in the previous segment, just want to highlight. Okay, now time has come, I shouldn't have used green, but that's fine. Now time has come to flip this around and to confuse you, okay? Isentropic work divided, or rather, or power per actual work or power, right? Whichever one of them you're gonna use. So why did I flip these? I'll give you two options. You know, I mean, this class is too easy. I want to mess up with your mind and I want to cut points, so I'm doing this kind of slick move to, again, mess up with your brain. That's option A. Option B is this: efficiency. Efficiencies 0, turbine. I explained this, but I still want this to be here as well. I want this being this and this. And let's think about this. This is a compressor, so I'm paying for it. So this is the refrigerator. Let's say I have absolutely the best refrigerator in terms of the efficiency. Am I gonna pay, like, let's say I paid for that for $10, right? Actually, I'm gonna pay more, right? In actual case, I will pay more to the electricity. Let's say it's gonna be $12, right? Again, this is proportional to the power. I'm just putting in terms of the dollar sign so we can talk about this easier. So you can see I still obtained myself something between 0 and 1. That is the intention, not to confuse you. And don't worry, I have plenty of places to cut points from you, so you shouldn't worry about that at all, okay? HES minus HI divided by HEA minus HI. Why I flip this is, you can see over here, this is how it's written, exit minus inlet. But that doesn't really matter. You realize that, right? You know, if you simply by mistake write an HI minus HES, and obviously you have to do both numerator and denominator, you're going to get a minus of it, but minuses cancel, so it doesn't really matter. You can memorize. The only important thing is that this actual is down here, actual is up here for that, and the nozzle. Okay, that's what I want you to know. And again, I need for this guy, I need two, properties, just like what I did over there. So this is going to be P2A will be P2S. Now, as you can see, these look very similar, so I'm going to solve one question. Why? Well, it's too long, okay? I'm getting a little tired, to be honest with you, okay? So I'm going to solve one question. We can, once I solve one question, it will be very clear what I'm trying to accomplish in this particular question, okay? Let me come back. I don't want you to watch me write several sentences, so I'll be right back with the question statement. Just give me 1 second, please. Okay, I'm back. So, nice and easy, the question seems. What is the isentropic efficiency, to the point, of a steam turbine? Okay, that's a turbine, not a compressor, doesn't matter. If steam enters, okay. So what it says is, I have the state 1 entrance to the turbine as 500 psi A. This is my P1, and my T1 is also 800 Fahrenheit. And in the second, okay, the state is also known. Such an easy question. PSI A, T2. I'm joking about such an easy question, but I gave you the state 1 and state, or rather the inlet and the exit of the turbine. Okay. So what I will do is I will go to this is a steam. This is not air. Students use this, ideal gas tables to read steam, which is not gonna be awarded much, if at all, partial credit. Okay. I have to go and visit the steam tables. And those are, as you know, it's table A5E, A4E, A6E, etc. Okay, so now I want to establish, I first go to table A5E and I look at my pressure, because that's a pressure table. I look at 500 psia, right? And I read my saturated temperature for that particular case to be 467.04 Fahrenheit, okay? And the temperature that's given to me is higher than that, so I know that I'm in the superheated water region. So now I go to table A6 and read that. I have 500 psia and I have T is equal to 800 Fahrenheit, and I find that particular number, and H1 turns out to be 1412.5 BTU per pound mass, okay? And while I'm there, you may not appreciate why I'm writing this, because you're gonna deal with entropy and all, so I wanna get S1 too. I'm pretty sure I will need this, 6576 BTU per pound mass times Rankine. Careful about the units, okay? Okay, so that is, basically one. One is coming between, and I have two in terms of, this is actual, and I have 2S, right? And the 2S is P2S is equal to 15 psia, and as you know, S1 is equal to S2S, right? You see, now I have, like, instead of 2 states, I have 3 states, and I can find the efficiency that way. The reason is, up there you see the turbine efficiency is HI minus HE exit divided by HI minus HES, right? I now know this. Now I will proceed with the exit stuff, which is not too bad, okay? You'll see. Let's go to 2A, so I can find that. So again, I go to table A5E, and I pick up 15 psi, that's what it says, and I find my saturated temperature to be 212.99 Fahrenheit, okay? So what does this mean? The temperature that is given to me is what? 240, that is higher than it. So I'm still in the superheated water region, so I still need to go to 6A. And I'm not as superheated as the previous case, but I read this particular value, right? 240 Fahrenheit, not a big deal at all. I read this H2 to be 1163.9 BTU per pound mass, okay? So that is pretty much the H2A, okay? So I get that one too. Okay, now I will go to 2S, okay? I think I'm proceeding nicely, no? Again, let's have the P is equal to 15 psia, and S1 is equal to S2S is equal to, I write it there, 1.6576 BTU per pound mass times Rankine, right? And I look at the table A5E. Why am I looking at table A5E? Is I want to establish where I am. I don't really know where I am. So I look at this SG value, and I find it to be 1.7549 BTU per pound mass Rankine. So what does this mean? Where am I in terms of the steam dome, right? So you can see SG is larger than the S2S, which means that I am in the zone 2. Remember, I numbered the zones like this. 1, 2, and 3, right? I was in 3 for state 1, state 2A, state 1, state 2A, and state 2S is in the mixture zone. So now I will do as SF also needed. So that's 0.3170 BTU per pound mass times Rankine. So I have my S known, SF plus X. Remember this business? Not fun, but it is a business. 1.6576, 0.31370 plus X times 1.4441. So from here you can get your X to be 0.93. Note that basically this is the SFG, right? So which is SG minus SF, and that's also written in the table A5, so you can directly get it, okay? All right, now I know this, so now I have to find the H, right? H, let's call it S, will be HF plus X times HFG. So I have to get my HF value, which is 181.21 BTU per pound mass from the same table. HFG is 969.47 BTU per pound mass, right? So now I plug this in here, 181, what was it, 21 plus 0.93 times 969.47, and then my HS turns out to be 1083.22 BTU per pound mass. And now all is left is to simply find this HI minus HE actual divided by HI minus HES, which is this, by the way. This is HES too. So let's write it. 1412.5 1412.5 minus minus. The actual is 1163.9. The S is right up there, 1083.22. And then you calculate this, you get to 0.755. So it is 75.5% is the efficiency, isentropic, important efficiency of this particular turbine. Okay? And the turbines typically have 70 to 90% isentropic efficiency. This is within that ballpark. Thank you for watching this. Have a great day.